Hello, and welcome to the second part of my new series talking about why we cut trees, otherwise known as silviculture. In the first part, I got a little philosophical, but in the second part, we're going to be a little bit more grounded. But I don't think that we can quite get to the point where I can say, like, oh, this is why I'd clear cut this forest, or this is why I'd use a shelter wood here. Before I actually talk about the different ways in which we cut trees, I think it's very important that we understand how trees grow. So in this section, I'm going to be talking about how trees grow, because this is kind of essential to understanding how you might want to cut them down. So I'm going to break this up into three sections here. The first section is going to be just talking about, in general, how trees grow over time. Now, trees grow over time along an S curve, and I've mentioned this in previous videos, so I apologize for some rehashing here. But what I mean by that is that over the course of time, trees will grow slower at first. So, when they're very little seedlings, they'll grow fairly slowly because they're pretty small trees, of course. Then they'll reach kind of a middle-aged point in which they'll be growing very, very fast. This right here is kind of a middle-aged tree in its peak. And then finally, as the tree gets older, it'll kind of start to slow down. It'll grow less. Now, when I say growth, I mean growth in terms of both timber and in terms of carbon dioxide. So, trees remove most carbon dioxide during their middle age period, and that can depend on the different species. But generally speaking, there's a multi-decadal window between like 15 and like 50 when a lot of trees are kind of in their prime. Now, there's a couple things to note here. This occurrence, this S curve, occurs for both individual trees and for forests in general. So at an individual tree level, trees obviously grow slow at first because they're very young and they're not very big, and so they don't have much like photosynthetic capacity. They kind of reach their optimal age and grow really, really well when they're kind of like middle-aged, like this one. And then when they get older, they start to slow down again. And why is that? Well, trees do have a lifespan. With a few minor exceptions on the West Coast, like redwood trees usually have a lifespan of like a couple hundred years at most. And so when trees start reaching the end of their lifespan, what happens is that they have to devote more of their resources to just kind of staying alive. We call this maintenance respiration. So when trees are really, really big and really old, they occupy the same amount of space in terms of the canopy. So they're sequestering basically the same amount of light. They're able to perform basically the same amount of photosynthesis, but they have a bigger trunk and they have an older trunk. And so they have to kind of put more energy into maintaining that. So they have to kind of put more energy into fighting off diseases that are creeping, into its bark and in their wood. They have to put more energy into kind of surviving loss events like big old branches kind of falling off. So as trees get older and as they reach their lifespan, they slow down and they don't grow as fast. And the same happens for forests in general. So at a forest level, when a forest is brand new, it's not going to sequester very much carbon because, again, the trees are just not very big. They may be like suffering with competition with other species that are like raspberries or something. When they get to middle age, forests are usually their most productive. And then when they get to older age, forests kind of slow down and they don't sequester carbon and they don't continue to really accumulate wood. At least not very much. And the reason for this is that old growth forests are a relatively steady state system. And what I mean by that is that as trees get older, they start to die. And so trees will die in these old growth forests and they'll leave gaps, and then new trees will come in and take their place. And this forms a cycle in which old growth forests are continuously kind of replenishing the trees in their forest. Dead trees will fall down, they'll decay, that carbon will go back into their atmosphere, the timber will be lost. And so old growth forests, they do remove carbon from the atmosphere, and they do grow a little bit, but not anywhere near as much as like a middle-aged forest because they're kind of in this constant replenishment rate. And I think this is one of the biggest misconceptions about how forests work, because a lot of people think that like the Amazon rainforest is constantly removing tons and tons of CO2 from the atmosphere. It does remove some, but it doesn't remove as much as like a middle-aged forest like this size. And we can just think of this like intuitively speaking, if the Amazon rainforest were just continuously pulling carbon dioxide out of the atmosphere forever, like where would that go? Like the Amazon rainforest has been around for 55 million years. If it were just constantly sucking CO2 out of the atmosphere, I mean, we probably have like an Amazon mountain instead of an Amazon rainforest. So there's not even like the outflows in these systems for the rate of sequestration that like a middle-aged forest is able to achieve. So we've got this S curve. Typically speaking, if you're looking to manage optimally for either timber or for carbon, the best time to harvest your trees is usually a little bit after the inflection point of the S-curve. And when I say the inflection point, I mean kind of the midway point at which growth kind of starts to slow down a bit. And the reason for this is, if you hit it a little bit after that inflection point, you're able to then replant trees again and start the process anew. And, most of the time is then spent in that peak growth period. So one of the ways to actually figure out if you're at that midpoint of the S-curve is to take repeated measurements of the forest. And if you take a bunch of measurements, like let's say like every year, or if you just take a tree core, for example, and see how fast the tree has been growing each year, you can see how, where you are on the S-curve, like how fast the tree is growing relative to last year. And one of the ways that foresters decide whether or not it's time is basically to look at the annual growth rate and compare that to a longer period of growth rate. So they'll look at how fast trees are growing within a year, called the mean annual increment, and they'll compare that to how fast trees are growing over a period of 5 years. And generally speaking, when the two lines start to converge, that means that you've crossed your inflection point, and that means that it's time to cut. Now, that's kind of the most traditional way of thinking, and that is the optimal way of getting the most amount of material out of the forest. So if we were all looking to use forests to suck up as much carbon dioxide as possible and not caring about anything else, that's how we do it. Likewise, if you were trying to get like the most amount of like biomass or pulp out of the forest, that's a great way of doing it. However, we have other considerations. So older forests offer a lot of other co-benefits, and one of these other co-benefits is that the products in larger trees tend to be worth more money. So timber is worth a lot more than pulpwood. And so a lot of the time it's actually worth waiting a little bit until you're getting a little bit closer to like the top of that curve to harvest your trees. Now, a lot of improved forest management carbon programs were designed around just this. Their principle is that if you can actually take a forest that was likely to be cut due to like pulp for like the most aggressive timber harvesting scenario that you can imagine, and then incentivize people to kind of leave their trees on their forest for a longer period of time, not only will you get a forest that is more, natural looking and generally better for the environment, a lot of the time you'll get more valuable timber products out of it. So a lot of improved forest management projects are just about kind of incentivizing people to leave their trees on their land a little bit longer than they typically would if they were just optimizing for pure volume or carbon or biomass. Okay, so that's the S-curve point that I wanted to make. But the second point that we want to make about forest growth here. Okay, so that's the first point that I wanted to make in this video. But the second point that I want to make is kind of more along the lines of how forests grow structurally. So generally speaking, forests kind of grow in 4 different distinct phases. And this can be tracked all across the world depending, no matter what type of forest you're looking at. So the first phase of forest growth is typically what we call the stand initiation phase. And as the name implies, this is an instance in which a forest has been completely annihilated and it's now growing back. Maybe it's growing back because we planted it. Maybe it's growing back because there was a wildfire or something. But the stand initiation phase is basically refers to when the trees are very, very small. Now, in the stand initiation phase, the biggest kind of threat to the forest is competition. So when trees are planted at first, or when trees are growing back from like a big disturbance, like a clear cut, other vegetation can often outcompete trees. Trees are made of wood, and wood is great, but it is a little bit slow relative to like a blackberry bush. And so trees are often kind of outcompeted against, other species that are a little bit better at colonizing these areas that are recently cut. So that's one potential caveat about the stand initiation phase. And one kind of defensive mechanism against that is that you will often see trees regenerating either in natural stands or in planted stands very close to one another. So you'll see really, really dense seedlings being planted in these areas that have recently suffered a clear cut, or really dense seedlings like popping back up. Maybe they're like, a couple, 20 centimeters apart on average. Now, when you go into a forest that's this big, you'll notice the trees are not 20 centimeters apart. So a lot of those trees that are initially, growing up during the stand initiation phase are going to die. But this is a really good way of kind of out-competing other vegetation because it kind of shades them out. Okay, so we progress from the stand initiation phase into the stem exclusion phase. At this point, the trees have gotten to a height where they're no longer competing with like raspberry bushes and stuff. And now they're at the point where they have to compete with each other. So in the stem exclusion phase, the trees are really in this like die-hard competition for light and resources. And so the trees are really densely planted next to each other a lot of the time. And they start to kind of just shade each other out. So they're racing towards the top of the canopy as fast as possible so that they can shade each other out and become the dominant trees in their area. As the name implies, in the stem exclusion phase, there's a lot of mortality. So this is where the big die-off happens from the really densely planted trees. Now, one important caveat to this is that the stem exclusion phase is not that efficient. And what I mean by that is that because the trees are competing with one another so viciously, they are not devoting all of their resources towards like peak growth. We really want the trees to put as much as their resources as possible into leaves so that, you know, they can sequester more carbon and they can create more photosynthesis. But in the stem exclusion phase, they're often competing in terms of height. So they're shooting up really like tall, skinny trees, or they're competing like underground in the root system. And this isn't necessarily optimal because we don't really want trees to be like wrestling with each other. I had a whole long tangent here about these people who think that like all trees love each other. But, you know, Darwinian evolution says that a tree would rather be on top of another tree. Okay, so the stand passes through the stem exclusion phase and a lot of trees start to die. We then get into the next phase. And then the next phase is basically the reinitiation phase. And what's meant by that is that the understory starts to reinitialize with new saplings. This is a critical phase to enable the forest to kind of continue perpetually. Now, the only way that this can happen is if during the stem exclusion phase, a bunch of trees die, right? And kind of leave a bunch of gaps that can kind of create a more uneven aged situation where there's sunlight getting to the bottom of the forest and new trees can kind of start to pop up. This forest right here, it's got a lot of invasives that are making reinitiation difficult, but it's in that phase more or less. Now, one of the risks here is that if you're replanting a forest, and, you know, let's say you're replanting, like trying to replant the Amazon or something, and you planted all your trees at once. They're all the same age, right? And maybe you didn't plant them all that densely. If the trees don't die, if some portion of the trees don't either die off or get cut down, you could risk a situation where not enough light is making it to the ground, and stem and reinitiation of the understory can't occur. And so you might notice that I'm suggesting in each one of these phases, silvicultural intervention, and by that I mean cutting down some trees, can actually be very beneficial for certain forests. And in this case, you know, if we're just replanting the Amazon and just walking away, which I think a lot of these reforestation projects are a little guilty of, there's a real risk that by the time these trees get to like 50 years old, they're all going to start to die at once, and there's not going to be a kind of a healthy replenishment of an uneven age system that can create a more natural forest. If they all kind of die off at once, then you could just end up where you started with like a big field of dead trees. So regeneration has been established, and now we're kind of approaching a more uneven age system. The last stage is kind of the old growth / mature stage. And this is the point at which trees are reaching their natural senescence. They're reaching the natural age in which they die, and they're starting to die, and they're starting to leave like gaps in the canopy. And there's a really robust kind of cycling of young trees and old trees kind of coming and going all at once. So this is kind of that peak old growth forest in which there's constantly some young trees out there and some middle-aged trees and some really old trees, and they're kind of constantly in this cycle of replenishment. Now, even here, we can imagine some scenarios where it's desirable to cut some trees. For example, if a tree is really, really old and about to die, or if a tree is kind of being overshadowed by another tree, it might make sense to come in and nip that tree out to capture that wood. Because, you know, if the tree's going to die, the wood's just going to decay anyway. So there are still these scenarios, even in kind of the old growth phase, in which some harvesting makes sense. Okay, so those are the 4 phases of tree growth. And we'll be referencing those phases as we start to talk about like why we might want to cut trees here and now and why we might want to not cut trees here and there. The last thing that I want to talk about that's really important. Okay, the last point that I want to make is, generally speaking, there are kind of 2 different reproductive strategies that we see in trees. There's shade tolerance and there's shade intolerance. So shade intolerance are trees that really prefer to grow up in full sunlight conditions. Now, these types of trees typically evolve in situations in which stands or forests are completely clear-cut or completely lost to fire or some sort of disaster. So in these situations where, like on the West Coast, where forests kind of very frequently burn down, the trees have evolved to be very good at growing up in full sunlight conditions in the hot and dry situations, and then kind of replenishing the forest from scratch. However, in these other environments in which forests are not really used to kind of being clear cut or burning down, like, for example, the Amazon rainforest, most of the trees in the Amazon rainforest are shade tolerant, or the east coast of the United States, or mainland Europe. Most of these trees are not evolved to do very well following some sort of massive disturbance. So if these forests burned down or were clear cut, those trees would not grow back very well. And this is really important because as we cut down trees, we really need to consider whether or not the trees that are going to regenerate after this cut are going to be capable of doing that in whatever we did. And so for this reason, on the west coast of the United States or the west coast of Canada, you see a lot of clear cuts because these trees are kind of evolved to come back after a wildfire. And so if you cut down these areas, you can typically kind of just either plant or just leave a seed source, and the forest will regenerate on their own very well. But in mainland Europe, in the Amazon, in a lot of like the moist tropical areas of the world, or on the east coast of the United States, if you clear cut these areas or if you set them on fire, the forest will not grow back. The forest may take many, many centuries to grow back, kind of maybe if ever. And so for this reason, you don't see clear cuts in these areas. Sustainable forest management in the East Coast or in the Amazon means basically selective harvesting, going in and cutting down a couple of trees and leaving shade for the next generation. And so this is kind of why you see clear cuts in some places and not in others. It's got more to do with how the trees reproduce than it does with necessarily like local laws or law enforcement. I'm sure that timber companies would prefer to clear cut trees on the East Coast if they were able to grow back, but they're not. Okay, so those are the three core concepts that I want you to carry forward into the later videos as we start to talk about like the different ways in which we cut down trees. Because, obviously it doesn't make much sense for me to say something like, and this forest would be applicable for a clear cut, because if you're not kind of thinking in the back of your head, oh, well, these types of trees are really good at growing back in cleared environments. Okay, I think we've covered enough for today. Thanks for tuning in.